Hi, welcome back. In this video we're looking at the P5 protection relays. Today we are going to break down exactly what you should do and why you can't afford to mix up CTs. First, let's look at the CT primary, technically known as the relay setting. This setting is for phase current transformers. These are three sensors that monitor the main load currently flowing through your L1, L2 and L3 lines. If you have 300:1 CT set on your phases, your CT primary is 300 amps. Now if you have in one CT primary in the software, this is labeled the in stand for residual or neutral current. This setting specifically is for A-fault CTs. These CTs is usually connected to slot A, terminals A13 and A14. They are to detect leakage to the ground. Even if your main phase uses 300A CTs, your air-fault CTs might be completely different. For example, 50 amps. Here are the main three things you should know. CT's primary monitors your load and detects short circuits between phases. In one CT primary monitors the spill current to detect earth leakage or ground faults. Secondly, they connect to different terminals. Phase CTs are going to terminals A9 through A12, while the in-one standard fault CTs connects to the A13 and A14. These settings are independent. You can have 1000 amps CTs primary for your heavy load, but 20 amps in CT primary for extremely sensitive ground fault detection. In software, you should navigate to General menu and Scaling view. You will see CT primary at the top of the phases, and further down you'll find the rated primary residual resistance settings. Getting those ratio right is the only way your relay will know if the 5 amps and its terminals means the normal load or fault. You should remember never energize your primary circuits until you have double checked these scaling values. If the relay is security guard, CT primary is like sensors on the front doors, while the in-one CT primary is dedicated sensors on the drainage pipe to check anything is leaking out of the system. They are both sensors, but they watch different paths and need a different calibration to work correctly. In CT1 secondary, we're looking at the primary current settings. We are zooming on the secondary side, specifically for the in-one input. If you ever wonder why I often choose 1 amps over 5 amps for air-fault protection, you should understand that one is more sensitive. The in-one CT secondary or in your setup software is rated output. While your phases CTs watch the heavy load, this input is connected to terminals A13 and A14 to catch ground fault current leakage. Depending on the CTs you installed, the P5 allows to configure this for 1 amps, 2 amps or 5 amps. However, if you're using the very sensitive air fault version of the relay, these settings fixed at 1 amps. Why then use 1 amps? Increased sensitivity. Air fault is highly independent network, can be tiny. A 1 amp secondary rating allows the relay to detect much smaller primary current than 5 amps ratings. 1 amp circuit has much lower electrical resistance or burden on the CTs in the P5. This keeps the measurement highly accurate without overloading the transformers. If your air fault CTs is located far away from the relay, the 1 amp signal travels much better over long wires without less energy loss. When you set this up, make sure that it matches the label on your physical CTs. If your CT says 50:1, your primary is 50 and the secondary is 1. Matching those in scaling views. Choosing the right rating is the difference between catching the fault early and missing it entirely. Checking your CT nameplates and setting it correctly and stay safe. Using one secondary for air fault is like using a microscope instead of magnifying glass. While magnifying glass 5 amps is great for looking at a large object, a microscope 1 amp lets you see the tiny details that are invisible for the naked eye, allowing you to catch sickness in the electrical network. Into CT primary. We already covered standard phases and air fault settings. Now we're looking at the in2 CT primary settings. This is for the special ops of the air fault detection, the very sensitive air fault input. Let's look how that's working. In the P5, in2 refers to the very sensitive air fault VS input. While the standard in1 input handles typical ground faults, in2 is designed for detecting tiny current leakage that standard transformers might miss. You'll find those wires connected in the terminal A15 and A16 in the slot A. The in2 CT primary setting defines the related primary current of your sensitive transformers. It is incredibly flexible here, allowing you to set the value anywhere from 1 amp to 200 kiloamps. However, unlike other inputs, the secondary for the specific channel is fixed at 1 amp to ensure maximum protection. So why would we set this to 50 amps? In high independence on isolated networks, a ground fault might only leak a few amps. A 50 amps primary CT allows the relay to see those tiny changes with extreme accuracy. Core balance CTs like CS series often use this lower primary rating to provide very high transformation ratio. If you are protecting a motor or transformer neutral point, 50 amp is a standard ratio for catching faults before they cause massive damage. In the software, look for the setting labels, match the exactly of the nameplate of your core balance CTs. If your CT says 50:1 type, 50, it's that simple. By getting it wrong means your most sensitive protection doesn't work. So you should scale it correctly and your protection will work at the smallest hidden faults. If standard air fault in one is like a smoke alarm that triggers when the fire is already visible, very sensitive air fault in 2 is like high-tech air sniffer that detects the single molecules of gas. Setting it to 50 amp is like calibrating that sniffer to be precise that even tiny scent of leaking electricity ensures to keep your system safe. We talked about phase CTs, but now we're focusing the inputs, also known as a residual or RF-CT input. Getting the polarity right here is the difference between a relay that protects your system and one that strips blindly or fails to see the fault entirely. Let's see the standard meaning. The other modes are need to know. Let's see what standard means. Polarity determines how the relay compares the angle of the residual current against the residual voltage. This is vital for directional air fault protection. If your polarity is inverted, the relay might see the forward fault of your line as a reverse fault behind it, meaning it won't trip when it should. In the P5 standard, polarity usually refers to default resistive res mode. In this mode, the relay accepts the fault current to be largely in the phase with the voltage pitch in common ground networks. Physically standard means your CT is installed with the P1 terminal facing the bus bar and the secondary wires connected correctly to the terminals A13 and A14. But not every network is the same. Here are other options. One is cap or capacitive mode. This is for unearthed or insulated networks. Because the leakage current in these systems is capacitive, the relay automatically corrects the angle by 90 degrees, so it can still determine directional accuracy. Res capacity mode. This is a clever dynamic setting. You can use this digital input to flip the relay between resistive and capacitive modes on the fly. Perfect for system where the coil might be temporarily switched out. If you have a network curved through the small resistance, you might use sector mode instead of simple half pane. This lets you define the specific tripping wedge like 70% to make the protection even more selective. No direction mode. This turns off directionality entirely, making the stage behave like standard non-directional overcurrent stage. What if the CT was wired backwards and it's too late to change the physical cables? The P5 has a software fix called angle offset. You can manually rotate the tripping zone from -180 to +180. Because it's so easy to swap the wires, the source state is mandatory to perform primary injection test during decommissioning. You must verify the angles on the image against the known power flow or to ensure polarity. Think of in-CT polarity like security camera with motion sensors tripwire. Standard mode is like setting the prior to catch people entering the front door. Cat mode is like adjusting the sensors for a side angle door, and angle offset is like digital rotating the camera view because of the bracket was installed upside down. Think of these settings like fitting a battery into a torch. The standard way is to putting the positive in first, the circus is complete and the light shines forward. The opposite way prevents the torch from working, or in the case of relay, makes the torch think the light is shining behind you. In the DCC mode, it's like a seesaw. The system is standard, balance, only when one side is up and the other is down. If both sides are on the ground at once, the relay knows the equipment is broken.